section 19.3 involving compound probability. So today we're going to be using the compound rule for AND. And that compound rule for AND means to multiply the outcomes of each event. So let's say in number 2, we're looking at the probability that both marbles will have strikes on it, and we're removing a marble first from the first set and then from the second set. So using the AND rule, we're going to first find the probability of the first event. So the probability of selecting a strike in the first set would be 1, 2, 3, 4, 5, 6, 7 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. The probability of getting a strike from the second set would be 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. The probability of having both of those occur is the product of those two. Now, when we use our calculator, we do not need to reduce any fractions. For example, we can put 9/18 in just as it is to the calculator, and we'll let the calculator do the reducing for us. All right, so we have 7/17 multiplied by 9/18, and that gives me this decimal. I like to change this decimal into a fraction. If I want to write it as a percent, I would leave this decimal as 0.205 or about 20.5%. But as a fraction, I'm going to go to my math and select fraction and enter once, enter twice, and I get a fraction of 7/34. And again, that's about 20.5%. There are 24 students in a math class, and each day the teacher randomly chooses one student to show a homework problem solution on the board. What is the probability that the same student will be chosen 5 days in a row? So the first day, to select one student, that's one favorable out of a total of 24 students. On the second day, the probability of selecting that very same student is still 1 out of 24. There's still 24 students in the class. On the third day, 1 out of 24. Fourth day, and the fifth day. 5 days in a row. And the probability of that happening is the product of all 5 of those fractions. Now, let's see if this will work on our calculator. Not sure if that denominator might be too big. Let's check that out. So basically, we're multiplying 1/24 to the 5th power. So what I can do is I can put that in as 1/24 raised to the 5th power. And yes, it's a very small number, as you can see from the screen. That E-7 means to move the decimal 7 places to the left. I'm not sure if we're going to get that as a fraction. Yeah. All right, so here's what we're going to do. We're going to mess with this. We're going to do 24 to the 5th power. And we know 1 to the 5th power, 1 times 1 times 1 times 1 times 1 is 1. So we have an answer of 1 divided by 7 million 962,624. The likelihood of that happening is not very likely. All right, so I notice in the directions on this page that we have the word dependent. All right, so let's talk a little bit about dependent events. Dependent events are different than independent events in as much as the second event is dependent on what happens with the first event. So let's take a look at number 6 and see how this is a dependent event. A bag contains 8 red ribbons, 7 green ribbons, and 3 yellow ribbons. If you randomly remove 3 of the ribbons from the bag, what is the probability that the first 2 ribbons will be yellow? So the reason why we call this a dependent is as we remove 1 ribbon, we do not put it back in. We do not replace it into the bag. So that drops the number of total outcomes. So that's why we call this a dependent event. All right, so let's take a look. We want to get 2 ribbons, and we want them to be the first 2. All right, so the number of favorable yellow ribbons is 3 out of a total of, let's see, 8, 15, 18, 3 out of 18. And we've removed a yellow ribbon now, so now there are only 2 yellow ribbons available out of a total of 17 ribbons. So the first 2 I have now selected are yellow, and the third one can be any color. It doesn't say here that it has to be a particular color, so it just says, I just want the first 2 ribbons to be yellow. The third one can be any number, so there are 16 ribbons left out of a total of 16 available to choose from. So basically the probability of picking the last one is 1. All right, and we're going to multiply and find the product of those 3 events. And I know 16 divided by 16 is 1, so I don't need to enter that into the calculator. I can just multiply those 2 fractions together, and that gives me a probability of 1 out of 51. And again, we have another dependent situation where we have a box that contains discs with letters on them, and we're removing 4 of the discs one at a time, and we're setting them on the table, and we want to know the probability that the discs we remove will be in the order A, then B, then C, and then D. So this is an and probability that are dependent events. And so we're going to start with removing an A. Let's check out the A's. We have 1, 2, 3, 4, 5. There are 6 A's out of a total of 16 discs altogether. All right, so now I've removed an A, and then I want to know what is the probability of then getting a B. So let's see, the number of favorable are 1, 2, 3. There are 3, but remember I've already taken an A out, so there are only 15 discs left. So now I've taken out a B. The next one I want to remove is a C. So we have 1, 2, 3, just 3. Looks like there are just 3 C's out of 14 discs. So remember I removed 2 already. And then the probability of picking a D for the last one, we have 1, 2, 3, 4 D still left. Make sure I didn't miss any 4. And there are only 13 discs left. So the probability of having this happen is the product of each of these And go ahead and put in the fractions without reducing them. And for number 10, it looks like we have some review problems to factor. And taking a look at A first. And this looks like it is a factorable trinomial, which means I must have 3x times x to get my 3x squared. All right, there are many ways to multiply to get the number 10 and arrange them in different combinations. So I'm just going to try and put 5 here and put 2 here. 5 times 2 is 10. But I need this to give me a negative 1. So let's see if I can get a negative 1 from that all of this. There's a 3 times 2. That's a 6. There's a 5 times 1. That's a 5. If my 6 is negative, that's a negative 6, and my 5 is positive 5, then that could give me a negative 1. And one of the things I should have done before I started this problem is I should always ask myself, is there a greatest common factor? And I was reminded of that when I saw part B here, because in part B, there is a greatest common factor. Both of those terms, this first term and this second term, both have a greatest common factor of 2. So we're going to begin by factoring out a 2. A little more room here. And 2 goes into 98 49 times. So we have 49x squared minus 1. So I factored out a 2 from each of those terms. I divided each term by 2. And so I'm looking at what's inside the parentheses now. And what's inside the parentheses is what we call the difference of 2 squares. And if we remember, when we factor the difference of 2 squares, we take the square root of the first term, 49x squared. The square root of that is 7x times 7x. And then we take the square root of the second term, 1. 1 times 1 is 1. And then we set 1 at positive and 1 negative. And yes, in part C, we have a greatest common factor. Not only do they have a 3 in common, but each of those terms also has an x in common. So we want to make sure that we factor out not only a 3, but also the variable x. So our leftovers gives me x squared plus 5x plus 4. All right, and I can check that really quick just by distributing. There's my 3x to the third. There's my 15x squared, and there's the 12x. So it looks like we have factored out correctly. And now what we can do is we can factor what's inside the parentheses. All of this is a factorable trinomial. And in this problem, I'm looking for 2 numbers that multiply to 4, but add up to 5. The 2 numbers that multiply to 4 and add up to 5 are 4 times 1. So we have